So most of the earthquakes are going to occur along fault, and that energy is going to build up, and then boom, the earth is going to crack, and the earthquake energy is going to radiate from that point. It's going to happen along a new fault because it broke those rocks, or maybe there is a pre-existing fault that has friction on it, and then the movement is going to overcome that friction, and then the fault is going to break again. So either way, it's going to be a zone of weakness. It will remain always a zone of weakness because those rocks are going to be crushed up in that fault zone. So this cartoon shows what that might look like. The C-clamps are on a piece of wood there, and if we're moving those clamps in a block like this, there's going to be small cracks here in that piece of wood. It's going to accumulate that deformation along that zone where those little cracks are forming. Eventually, the movement and the stress on that rock, and in this case the piece of wood, is going to overcome the strength of that rock, and then it would break, and we'll call that the rupture. It's going to exceed the strength, the movement, and the bending. We're going to exceed the strength of, in this case, wood, but really rock, exceed that, and it's going to break. We'll get to a point of failure, and then that piece of wood, it like snap back, right? So rocks are going to do the same thing. They're going to be deformed and snap back into place, a deformation after the earthquake occurs. So here's an image showing that we're really sliding two things past one another. The rocks slide past one another along a fault. The fault motion cannot occur forever. The fault motion is arrested or stopped by friction. We're trying to slide two rocks, this way, slide two rocks by each other, they keep getting stuck, and then they're going to slide past one another. So in the figure here, time is increasing towards the bottom. So this block is the rock, and it's at rest, and here is a coil attached to it. We're going to pull that coil. The rock is still going to be at rest until the elastic motion within that coil can't really go any further. It's still building up that stress, and eventually that rock is going to slip. That slipping is the fault motion. Your hand keeps moving. The rock is at rest again, friction against the table underneath it. It's going to move again. And that's how fault motion occurs, is we're going to build up that stress. It's going to move. Build up that stress, move. And the movement there is the fault occurring and the release of that seismic energy. So those little cracks that were occurring in that piece of wood, those are going to be the foreshocks. So it can be little events that foreshadow the main event. After an earthquake occurs, maybe the largest shaking event, there's going to be aftershocks after the large earthquake. And those aftershocks can be pretty big, or they can be kind of small, and they can occur for weeks or years after the main event. The image below shows the earthquake that shook in 2011 near Washington, D.C. And the color coding here is showing time since the main event. So the orange or red ones were soon after, within the hour after the main earthquake, and then yellows and the greens occurred days or weeks after the main event. Faults can move without generating earthquakes. So brittle deformation occurs, and then when the faulting and that buildup and the release of that energy. But rocks can also deform ductily, kind of plastically, or there can be movement along that fault with no friction. So this happens deep within the earth, 15, 20 kilometers in the crust. Rocks are going to be hot. They can just kind of flow with that motion, and there wouldn't be an earthquake associated because it would be ductile versus brittle deformation.